So in our final video about vectors, we're going to be talking about the mathematical addition of vectors. So let's say I don't really have a protractor and I want to do it that way. Also, protractors, we are doing measurements, we're encoding in error into our process. What if we want exact answers and the math can give us our exact answers? Now, I will say, even when we're doing the mathematical process, even if we don't do a scaled vector drawing for that, we're still going to be doing some drawings because we want to be able to sense check our answers. It is preferable, I will just say flat out, to do a full-on graphical addition of the vectors and then check it with the math. Doing both processes is always preferable to doing just one, because as you know, you're more likely to know that you've made an error if you can't get your two processes to converge. So what we're going to be doing is we're going to be looking at each of the problems that we've studied through this video sequence: the 2 meters east, 5 meters east, 2 meters west problem, the 5 meters east, 10 meters south problem, and the 10 meters at 30 degrees north of east, and the 50 meters at 45 degrees south of east problem all together in order to come up with our answer. So here we go, and we're going to jump on in. And so this page is going to be for our process, and then we'll do our problems on other sheets of paper. So the first process that we're going to do is we are going to sketch the problem. Right now, I would say that you might want to do a scaled diagram is the gold standard, but if you're not going to do that, you're at least going to sketch the problem. So going back to our original problem, let's say this is our A is 5 meters east and B is 2 meters west. I'm still going to throw a north, south, east, west compass rose onto the page, and I'm not going to pick up my protractor or my protractor, just the protractor. 5 meters east, 2 meters west, and then there's my answer, A, B, R, right? So that's going to help us sense check. Okay, so since we're not doing that, the scale process, I'm just going to leave it at that sketch. Okay, so the next thing that we're going to do is we are going to understand that when we are adding vectors, there's a very specific process that we have to use. And there are certain types of things that can add together effectively. Like, for example, if I said to you, what do you get if you have 3 apples and 4 apples? Well, you'd very clearly say, I have 7 apples. But if I said, what if I have 3 apples and 4 oranges? You're like, well, apples and oranges don't mix in that particular way. Now, a snarky person might say you have a fruit salad, haha, but there's some truth to that, actually. There's a way to make apples and oranges mix if you have some sort of common thing that I can put them into. But otherwise, those two things are immiscible, right? Because we can only add together like types of things. And we're going to keep that process in mind. So the second thing that I'm going to do with my process is I'm going to make declarations of positive and negative directions along each relevant axis, right? Because in our present problem right now, we have one relevant axis. It is the east-west axis. We don't care about the north-south axis because we have no quantities that lie along it. But east and west are not mathematically relatable terms, right? You can't add east and west, but we can think of the east-west axis like a number line. And I'm going to make, I don't know, east positive and west negative. Now, there are going to be some problems that I might want to make west positive and east negative. We don't want to be slaves to Descartes, right? Just because Descartes made the positive x-axis pointing in the same direction that we would normally put the east axis through the compass rose, doesn't mean that the positive x-axis has to be the one that's to the right. You can have the positive x-axis being the one to the left if you want, right? You're just doing a rotation from the Descartes the Cartesian coordinate system, and that's totally acceptable. We don't want to be overly constrained by that. In fact, there's going to be plenty of times when we're thinking about a vertical axis that I want down to be positive. For example, if I drop something, what direction does it move? Down. What direction is acceleration? Down. What direction does gravity act on it? Down. Why in the world would you make up positive just to like be consistent with some sort of norm when you can impose on your page a directionality that makes problem solving better? I don't know. Maybe that's just me. Anyhow, we've now made our declaration. Cool. We are going to skip step 3 because for this particular problem, step 3 doesn't happen. Okay. And we'll see why a little bit later, right? Step 4, all right? So there are sort of 2 ways to do step 4. What we're going to want to do is set up equations or a methodology for doing a vector addition along each relevant axis. So set up an equation or methodology for doing the collinear addition of vectors along each axis, right? Because north and south always mix. East and west always mix because they are along the same axis. You know, if you kind of think about it in terms of equations, if I had an equation that had 2x plus 3x, you'd say 5x. 2x plus 3y, nothing. But if I had 2x plus 3y plus 2x plus 3y, you'd be like, okay, well, I have 4x and 6y, because I can always mix the x's and I can always mix the y's. It's going to be the same thing here because those x's and y's, you know, graphically are just things along different axes. So what's that methodology going to look like? Well, there's a couple of ways I can do this. The first thing I could do is I can write an equation. So in this case, R is equal to A plus B. Normal here. But notice I have easts and wests, but I'm not going to do that. What I'm going to do is I'm going to rewrite these things in terms of, well, east is positive, so plus 5 meters. And west is negative, so negative 5 meters. So I can say that R is equal to, now notice what I'm doing is I'm plugging in for the A, plus 5 meters, and then plus negative 2 meters, and I have that it is positive 3 meters. Now, notice here, I actually wrote the plus. We know that when you have a plus sign in front of something, that you don't actually have to write it, it's implied. But in this case, since plus means east, we want it explicitly in the problem. Now I'm going to decode that. In this paradigm, that means east, so this is 3 meters east. And there you go, I have the answer. Okay, now there's another way to do this. I can set up the equation a little bit differently. I can say R is equal to, and what I can do here is apply my declaration to my variables. So what I'm going to do here is just I'm going to write down a string of magnitudes. So the magnitude of A and the magnitude of B. And so what I'm going to do here is now I'm going to apply the declaration to each of these terms. I know A acts in the positive direction there, so I'm going to put the plus there, but B acts in the negative direction, and I'm going to put the minus there, right? So it's just sort of about where you use the declarations. In this methodology, I use the declarations in the plugin, but in this methodology, I use the declarations when constructing the equation, right? And so then I would put in plus 5 meters, since 5 meters is the magnitude of A, minus 2 meters, since that's the magnitude of B, and I get the same result of plus 3 meters, and that plus means east, okay? Now notice here, there's something people mess up in this methodology. This is not the magnitude of R, because the magnitude of R is composed of positive the magnitude of A minus the magnitude of B. So this vector R has directionality as an endpoint, all right? So there's yet another third way that I can organize this. I can do this in a table form, right? And so here, I'm going to have the vector, and here I'm going to have the value. So I'm going to have A, B, and then R. And so I ask, well, what is the value of A here? Well, it's positive 2 meters, minus 2 meters, or positive 3 meters. And therefore R is 3 meters east, because that's what that positive sign means. Okay. So what did I do then? From here, I set the equation for doing collinear addition of each axis, and then I found the answer and reported it with units. That's going to be down here in the bottom. I'm going to leave a little bit more because collinear vectors are super easy. When we have non-collinear vectors, that's going to be the rest of the steps that we're going to add to the process. But we're always going to end with an answer with appropriate, explicitly stated directionality. Okay, cool. Let's go to the next problem, and then we're going to see how this gets a little bit more interesting. And so that is, now I've got A is equal to, whoops, that's off the video, 5 meters east, and B is equal to 10 meters south. I'm going to draw in my little compass rose, east, south, north, west, and I'm going to sketch it. So that's east this way, west, south this way, A, B, and I know that that is R. Okay, and that is then theta R. Okay, cool. So once again, that was my first problem. Now, make declarations. I have two axes that are relevant because in my knowns, I have vectors that run on different axes. So I'm going to make east positive, that means west is negative, but I'm going to make south positive and north negative. Why am I not making north positive? Well, because my vector runs south, so why make it negative? Adding in negative signs that don't, no one likes negative numbers, right? No one likes negative numbers. So if we can avoid them, let's just avoid them. Sometimes you can't avoid them. Oh, well, but that's your decision. It's your decision. All right. So we've done that process. So good, 3. I'm going to still tell you, don't need step 3 in the process. So set up an equation or methodology for doing the collinear addition of vectors along each axis. Now, here's the problem. I don't have to do collinear addition because I've only got one vector along each axis. So how am I going to find R? Well, I think everyone knows that I'm going to use Pythagorean theorem to find the magnitude of R. But I want to put this in a very particular structure because I don't want to immediately rush to Pythagorean theorem because Pythagorean theorem is not generalizable. Okay, because if one of my vectors is not along one of the axes, then if my next step is always do Pythagorean theorem, I don't know how to do that. So I'm going to set up an equation or methodology for to do collinear addition along each axis. That's what I'm going to do. Because what I'm going to recognize here is, remember, when in the last video, I talked about components. If I look here, and if I would say, well, what are the components of vector R, right? What are the parts of vector R that lie along the axes? I think you'd very clearly see that they match up with A and B, right? So if we want to think about this, the horizontal component of vector R is simply vector A. And the horizontal or the vertical component of vector R is simply vector B, right? So that means that Rx is this positive 5 meters east. And this is the positive 10 meters, but that means south. So that's a problem in and of itself as well, mixing south and east. But I always know here, folks, that vector R magnitude, because of the Pythagorean theorem, is going to equal the square root of vector Rx magnitude squared plus the magnitude of the vertical component squared, because we know that the x and y components for any vectors are always perpendicular to one another, meaning that I can always use Pythagorean theorem. So now that I've identified that Rx is A and Rx is B, that means I have my Pythagorean theorem already set up. But I'm going to put this into a chart or a table, because remember that table I did in the last one? I'm going to expand this out because we want to set up an addition or methodology for the collinear addition of vectors along each axis. So I'm just going to make two columns. I'm going to have the vectors here, x and y. So A, B, and then R. So if I were to ask myself, well, vector A, how much of vector A goes in the x direction? I go, well, all of it does, right? All positive 5 meters of it does, because positive in this case means east. And how much it goes vertically? Well, nothing. Okay. And then vector B, well, how much that goes in the horizontal direction? Well, nothing. And how much of it goes in the vertical direction? Well, all of it does. And it's positive 10 meters because it's 10 meters south, right? And if you notice now, I have positive 5 meters as the x component of R and positive 10 meters as the y component of R, and I can throw it in this equation, which is identical to doing radical a squared plus b squared in this particular case. But now we've actually uncovered them as their identities of Rx and Ry. So our steps that we're adding here, step 5, is that we set up the equation methodology to do collinear addition of vectors in each axis, and then we're going to find Rx and Ry in each case, right? When the two vectors are perpendicular, that's pretty easy. One of them ends up being Rx and the other ends up being Ry, and then it's merry and it's happy, right? But sometimes that's not true, which is why I want a generalizable method. So the next thing in our method is going to find the magnitude of vector R by doing Pythagorean theorem with the components of the resultant. So I'm going to come back over here and I'm going to do that. I'm going to plug in the square root of 5 meters squared plus 10 meters squared. Pick up my calculator there, and I realize I've got the square root of 125. I'm always just going to write that down because I like a little intermediate step. Notice I dropped the units there because I don't need the units in intermediate steps. So if I do 125 raised to the 0.5, I get 11.2. I don't want to go any more really precise than that. 11.2 meters. Okay. And now I have the magnitude of that resultant. Great. But I'm not done. I also need to find this direction. So that direction is theta r. So looking at this, what do I have? Well, remember that B in this case is the same thing as Ry, and A is the same thing as Rx. As long as our angle is the reference angle, Ry is always going to be on the opposite side of that triangle, and Rx is on the adjacent side, meaning I can use the arctangent of the magnitude of Ry over the magnitude of Rx. Ooh, I've got my little vector symbols here, in order to calculate that. Once again, this is assuming theta r is a reference angle, which we're going to assume. Okay. So there we go. The arctangent of 10 meters over 5 meters. And then I can put that into my calculator. So that is the arctangent of 2 or 63.4 degrees. And there we go. And then I can finish it off because here we go, folks. R is equal to the magnitude, 11.2 meters at the angle, 63.4. And how do I know what the quadrant is? Notice the X is positive, that's east from my declaration, and the Y is positive, and that is south. So it is south of east because it's always the vertical of the horizontal. And there we go. I have that answer. And if I look back to my graphical result, bam, 11.3 meters at 64 degrees south of east. That is really close, right? So I have a lot of confidence in the process that I use in order to do that, and the answers match. This is great. Okay, so let's see how this goes when our vectors become more complicated. We're going to redo that last problem and see what, oh, actually, let me just fill in the steps that we said. So 7 was to find theta r, which is the arctangent of Ry over Rx. And then 8 is state the answer in proper form, which is always vector r, or whatever the variable is magnitude at direction. And that direction, if it is along one of the axes, is just north, south, east, west, positive x, positive y, negative x, negative y. But if it's not along the axes, then I have to have an angle and a quadrant, right? Don't give me an angle and quadrant if it is along one of the axes, or what we will call an axial vector, right? Which leads us then to our last problem that we have to do. A is equal to 80 meters at 30 degrees north of east. B is equal to 50 meters at 45 degrees south of east. All right, cool. I'm going to put down my north, east, south, west. I'm going to sketch it. So we know that that looked like this. Oh, that's a terrible sketch. Drawing not to scale, obviously, but we can get a sense of what that drawing is going to look like, or what that picture looks like. Okay, so let's follow our steps. We have sketched the problem. Boom. Let's make some declarations. I know this thing is going to end up in the first quadrant, so I'm just going to make those two things positive. So for those of you that like north and east positive, you're welcome for this problem, but there you go. And now we have the mysterious step 3. And here's why we have step 3. Step 3 is anytime any of your givens are non-axial vectors. Notice in the previous two problems, my first problem, I had something along the east axis and the east-west axis, both of them. And in the second problem, one of them was along the east-west axis, one of them was along the north-south axis. Now I've got things all in between. This is where we need to see what's going on. I want to note a couple of things. Notice I have vector r here. If I were to think about the components of vector r, they would go there. Rx and Ry, those two vectors make that. What I want you to notice here, if I look at the components of vector A, right? So that might be here and here. So that's AY and then AX. And then here's BX and BY. Just from a graphical standpoint, if I do BX or AX and then BX, notice that gives me the same thing as RX. If I go up AY and then down BY, that gives me RY, right? So this is what I was talking about, that I want to do the collinear problems separate, but I can't do the collinear problems when I have non-axial vectors. So what I'm going to do is I'm going to break all the non-axial vectors up into their components so I can do collinear problems. The simplest type of problem. So the glory of this methodology is it takes a complicated problem and reduces it to a simple problem, or a series of simple problems that you then build up back to complexity, right? So let's do it. Step 3, find the x and y components of all non-axial vectors. Okay, so in this case, that's both of them. So I'm just going to go, well, I need to find AX. Well, that's going to be A, magnitude of A, cosine theta A. Boom, that's 80 meters, cosine 30. We already found that in a previous video, so I'm just going to remember that that was 69.3 meters, not pulling that off of, not going to recalculate that. Then I'm going to find the Y component. AY is magnitude of A, sine, since AY is on the opposite side. Wow, total brain blip there. When my vector, when the angle is drawn as a reference angle. And so that's 80 meters sine of 30, right? Because remember, this is always going to be the reference angle unless otherwise stated. That's why the Y component is on the opposite side in this case, and that's 40 meters. And I'm just going to make a nice little pattern here. BX, B cosine theta B. So that's just taking the parts, 50 meters, cosine of 45 degrees. Plop that in my calculator. Oops, 50 cos 45, 35.4 meters. Okay, and BY is going to be B sine theta B, or 50 meters sine 45. And I know cosine and sine of 45 are the same, so 35.4 meters. There we go. Notice I just did it. I cranked. right? You should get very comfortable calculating the components of vectors so you can just do it. So the next thing I need to do is I need to find Rx and Ry. How am I going to do that? Either I'm going to do that by setting up equations, or I'm going to use my table. I always like to use the table, but if I was going to set up equations, I would do Rx is equal to AX plus BX, and Ry is equal to AY plus BY if I want to do it this way. And then I would plug in, I go AX. Well, AX acts in the positive direction. So that's going to be a positive 69.3 meters. And BX acts, well, also in the positive direction, because that's east. So positive 35.4 meters. And I can do that. And down here, AY. So that's going to be, well, AY acts in the positive direction, positive 40 meters, plus then BY will act in the negative vertical direction there. So negative 35.4 meters, and there you go. Or you set up the table of goodness, as I like to call it. So here we go. I have one row for each vector. If I have more than two vectors, I just keep adding rows, and I have a column for the X components and a column for the Y components. And I say, how much of this vector goes in the positive, or rather goes in the X direction? Well, the whole component does 69.3. And then I say, okay, well, that is east. So that's positive. And then let's say the X component of B, well, that's 35.4 meters. And I say, well, BX also is east and that is positive. So notice I separately think about the magnitude in each place and separately think about the direction. I find I make fewer errors that way. And so now the Y direction, we know that the length of the component is 40, and that goes in the, because of north, goes the positive direction. And then this is 35.4 meters, and that goes negative direction. And then to find Rx and Ry, I just add the columns. So I've got then 404.7 positive, and I've got here 4.6 meters positive, right? So that's already going to tell me that the resultant is going to be acting in the east direction and north. So it's in the north of east quadrant. But now I need to find R, the magnitude of R. I'm going to use Pythagorean theorem, Rx, Ry squared. And I just take the results from the columns right there. And I've got the square root of 104.7 meters squared plus 4.6 meters squared. Notice I didn't put a positive or a negative here because I'm just asking the magnitude. I get rid of the direction because you can't, like if I had the direction here, that's like saying east squared. Like, what does that even mean? It means nothing. So here we go. I can throw all of this into my calculator, 104.7 squared plus 4.6 squared. If you're like me and you don't trust yourself, I'm just going to throw in a little extra step there, right? I'm not going to like erase my calculator or anything like that, but I like to jot that down and then raise that to the 1/2 power, and I get 104.8 meters, okay? And then finally, theta r, inverse tangent of Ry over Rx. There we go. And then inverse tangent of 4.6 meters over 104.7 meters. And you can tell that that's going to be like a really tiny angle because we know a tangent, inverse tangent of 1 is 45. So something with a small number is going to have a small reference angle. So I find that, second tangent, second answer, plop that in, and 2.5 degrees. Pulling it all together, that means R is equal to 104.8 meters at 2.5 degrees north of east. Box it. Let me pull out my graphical answer. Boom, 105 meters at 3 degrees north of east. Oh my God. Beautiful correlation between those two things. I have a lot of confidence that I did the right thing. I'll just note something actually from a notation standpoint. I started getting a little lazy here with not putting my vector symbols over that. That's fine. Okay, that's fine. I actually held it together for 4 videos. I was very impressed with myself that I did that. I'm not going to get too picky about putting the vector symbols over things. If we're being really formal in class, we're going to do those vector symbols to make sure we know it. But in doing practical problem solving, it's just another thing to write, and it gets annoying at the end. So I guess that's sort of a nice thing I can say at the end, that, you know, at some point, formalism is for the sake of formalism, and sometimes we're just doing down and dirty the problem. But here we go. Now, what I want you to really notice about this is there's a lot of work in this, right? There's a lot of steps that happen. Everything is structured in its own way, in its own place. I got my drawing up front. I have my components. Now, by the way, I don't need to do both of these. These are the same step, right? Just two different ways of doing it. And then I wrote this, and I wrote this in the answer. Nothing's crowding. Anyone could read this and be able to think through and see your thought process, right? Really being able to do that and show your thought process is what we're doing. But at the end of the day, these are your 8 steps solving any vector addition problem, no matter how difficult the problem is, no matter how many vectors it is. And that's where we'll leave you, because that is a primary skill that we're going to need to know how to do in this course. The notion that we can't mix X's and Y's. That's going to be critical for understanding. Apples and oranges don't mix. Remember when I said back, how do they get together to become fruit salad? Well, the Pythagorean theorem is this interesting thing that since these are both length type measurements, I can put them together into its own different thing. But really, just like the dirty little secret of what we did here is we went from, and you might know this from your math class. Did you learn polar coordinates? Yeah, that's what this is. This is a radius and an angle. So I went from polar coordinates and I turned it into Cartesian coordinates, because Cartesian coordinates add really nicely and easily. And then we turned it back into polar by doing this, doing coordinate transformations. So the dirty little secret is what I've taught you is doing multiple coordinate transformations sometimes makes a complex problem really simple. So, well, not really simple. That's a lot. A complex problem, more manageable. That's the right way to say it. So with that, you have all the skills you need. Now you just need to practice.